Okay, yesterday was kind of a big day. We learned how to do arithmetic with infinite numbers. We learned the symbol aleph. We learned that aleph plus any finite number was aleph, that aleph plus aleph was aleph, that aleph times any finite number was aleph. And we were working on aleph squared, and apparently have proven that aleph squared is equal to aleph. I want to go through that proof yesterday, and you were going to look at another possibility today, overnight, and then I think we'll see a third possibility today. Peyton, I erased your quote. I'm going to try to remember exactly what it was. Something like different sizes of infinity would be very intense. Is that what it was? Something like that.
It'd be like a new concept or like an interesting concept that like I haven't really like been able to wrap my head around, but I think it'd be cool to like delve into that.
Well, we haven't seen it yet. So things haven't gotten that intense yet. I'm going to ask you in a minute if you did your homework and you found out another way to get that marching band off the field. But short of that, are there any questions on yesterday's class? Okay, I want to go through the quote unquote evens method that kind of came out in discussion with Charlie yesterday. I had an interesting thought on it last night, and I want to show you a slightly different take on it. It's the same proof, but an interesting thing is happening that I didn't notice yesterday. So here we are. We have the aleph by aleph array of counting numbers. Aleph columns, each with aleph many members. And we want to line them up with a single one-dimensional aleph. And Charlie was talking and she said something about you pair it with the evens. And I don't remember quite what happened, but one thing led to another, and then we started getting evens and evens and evens. And if you remember, it went something like this. This column, and actually, I apologize. I don't know whether 0 was included yesterday. So this column gets paired with these elements. Right? And I want you to notice something, because something reminiscent of Zeno happens. What we've just done is taken half of the numbers. Now this column gets paired with the evens from among the remaining numbers in the list. And the evens start with 0. So yesterday, for some reason, 1 was kind of pesky and left out. But if we start with 0, this is the 0 number here. Skip 1, 2, skip 3, 4, skip 5, 6, skip 7, 8. Now, let's look at what happened. This column took half of the numbers. This column took half of the rest. This column will take half of the rest. 0, skip 1, 2, skip 3, etc. This column will take half of the rest. 0, skip 1, 2, and the rest. So this is sort of a Zeno breakdown of the natural numbers. We take half of the rest, we take half of the rest, half of the rest, half of the rest. And eventually everyone is taken at the infinite stage, and every one of the numbers in this array is paired with every one of the numbers in this row. And it is exponential, just as somebody hinted it was going to be, and I'm forgetting now who suggested infinite would be next. Was it you? No, it was Eli. He's not here today. But what happens is on the blues, they skip 2. On the reds, they skip 4. On the greens, they skip 8. And on the oranges, they would skip 16, etc. So the gaps go up according to powers of 2. Questions on this? I truly had never seen this before yesterday. It was really cool to come up with this. And lying in bed last night, think about it, when I heard the Zeno's paradox, Zeno's first paradox way of understanding it, it was even better. So this was a treat yesterday. It was a good day for me. I had never seen that before, and I learned something. So thank you. All right. So here's the marching band. We want to get them off in a line. I asked you to think about how to do that last night. Anybody figure it out?
I think I have
look it
a
up on the
solution.
internet. Did anybody figure it out?
I think I got something.
You think you got something?
I think, well, basically, I think of it as kind of like squares. So you basically take, first of all, you take the top left corner 0 off the field. Then you go one, I guess that's a column over, take that 0, but then go down 1, and then go left 1. And then kind of repeat that pattern, like that like triangle-ish pattern, and keep taking bigger and bigger ones out. So the next would be 0, 1, 2, 2, 2.
Hang on, somebody got kicked out. Charlie, you there?
Oh, I think I saw her have like the red bars for internet, so she might be lagging out.
Yeah, while I was admitting her, I saw her on the screen. Charlie, you okay?
Yeah, sorry.
It's okay.
Yeah, my computer was lagging really badly. Like it kept stopping and then like it's picking up like 10 seconds later. So I moved to my phone.
So you might have missed Yoga's explanation. Yoga, why don't you go through that again?
So basically, I would think of it as sort of like triangles or squares. You start at the top left, and then you go over a column. Basically, pick the first one in the column, go down 1, then go to the left, take that 1, and you kind of repeat that shape over and over for bigger and bigger, like column rows.
So your row becomes 0, 0, 1, 1, 0, 1, 2, 2, 2, 0, 1, 2, 3, 3, 3, 3, 3, etc.
Yep.
Okay, good. That'll do it, won't it? Did anybody do it a different way?
I did mine like very similarly, except I did it so like they take like the first top left 0, and you move one to the right on the second row, and you move one down on the first row. So you take that 0 on the right, then the 1 on the left. So then you take the 0, 1, 2, and you keep going in that line.
Like that.
Yeah,
Good. That'll do it too, won't it? So where Yogiv was kind of doing these little L shapes, Peyton does just a straight line and skips those corners and just does a line. That'll also work. So Peyton's looks like 0, 0, 1. I think Peyton's might be a little easier to read. It goes 0, 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, etc. It's a little easier to see what's going on. I'm going to guess we could come up with a formula for this. We could certainly come up with a formula for both of them, but I think this one would come out more easily. Anything else? So we've now seen two different ways to pair what we could call Aleph cross Aleph. With just one-dimensional Aleph. One of those was this evens / halves / Zeno way. One of them was Yogiv and Peyton's, and I'm sure others got the same thing. Kind of diagonal march. There is a third way that you might think of as more mathematical. I don't know. I don't want to, this is all mathematics, so I don't want to minimize any of them. Here's what I want to ask. Is there a way to break up the counting numbers? That's this setup here. Into infinitely many infinite sets which don't overlap and which together fill the set. Let me read it again, then I'll explain it, what I mean. Is there a way to break up the set of counting numbers into infinitely many infinite sets which don't overlap and which together fill the set? Here's what I mean by that. If you look at the counting numbers, you can break them up into evens and odds. Two infinite sets which don't overlap and which together fill the set. You could also break them up into multiples of 3, numbers which are numbers which are 1 more than a multiple of 3, and numbers which are 1 less than a multiple of 3. Multiples of 3, numbers 1 more than a multiple of 3, numbers which are 1 less than a multiple of 3. 3 infinite sets which don't overlap and which together fill the set. You could also do that with multiples of 4 and numbers not multiples of 4, multiples of 5, 6, etc. The question is, but in each of those situations, you've got 2 sets, or you have 3 sets, or you have 4 sets. Can you break it up a way that you have infinitely many such sets? I don't know how the breakup would go, but if you could do that, then you could take that first set and pair it with these, the second one pair it with those, the third one pair with those, etc. And then you'd have plenty of hotel rooms for all your guests. Who's talking?
Did we like already do that with the evens thing?
What do you mean, Lauren?
Like whenever we took every other and then every other of every other, like doesn't that make infinitely many sets?
This.
Yeah.
It did. It did. I hadn't thought of it that way, but it absolutely does. Even you're, Lauren, you're right. The even numbers, the multiples of 4, the multiples of 8, etc. Not exactly multiples of 4s, but every 4th odd, every 8th odd, etc. That would do it. You're right. You're right. There's another way to do it, which I wanted to talk about and wanted to see if my description suggested it to anybody. But Lauren is right. This does what I'm describing. Yeah.
This is, I don't know if this is what you were suggesting, but I'm thinking maybe multiples of primes.
Say it louder, Yogev.
Multiples of primes.
Multiples of primes. So what do you mean by that?
I mean that if you get with like primes go, we saw how primes get bigger and bigger to infinity.
Yep.
And so the fact is you can have like that they're primes, you can have like their multiples, and I don't think that would create a set that overlaps anywhere.
Think about the multiples of 3 and the multiples of 5.
Oh, yeah. Wait.
What would mess you up?
If you multiply by the other prime or by a multiple of that prime.
Yes. So where's 15 gonna go?
That's a great question, actually. Where would 15 go?
Okay. So multiples of primes is not the right way to go, but you're close. How could we avoid overlap? Can somebody help Yogev out?
What about primes and compound? Would that help?
Primes and composites, you mean?
Yeah, composites, not compound. Composite numbers.
Only 2 sets. That's only
We're-
2.
yeah, that's what I was thinking. Like we're still in a finite amount of sets.
Yeah. Go back to multiples of prime, Yoga. Refine your notion.
All right, so we got multiples of primes, but our issue is that it might overlap, which
Yes.
means we need to figure out how will we make it not overlap. Anyone have any ideas? Because I am currently stumped.
I mean, we could do like exponents of primes, but then that wouldn't fill the set.
You could put it in based
know?
off of
You don't need
like
to
its
fill it
largest
completely.
prime multiple.
Riken, make your suggestion again.
We could do exponents of primes like 3, like 3 to the first, 3 squared, 3 to the third, 3 to the fourth, and so on. But that wouldn't fill the set completely.
You
You
said
put, you,
powers of primes is what you mean.
but you don't need to fill
Yeah,
the set.
yeah, you know what I mean.
You don't need to fill the set. Like,
Hang on just a sec, okay? So list the powers of 2, Riken.
1, 2, 4, 8, 16, 32.
You better leave out 2 to the 0 because you're gonna run into trouble with overlap there, aren't you?
Yeah.
So just go 2, 4, 8, 16, yes?
Yeah.
And the 3s?
You're making me do this. 3, 9. Oh no.
Come on.
27.
Yeah, 27.
Help me out, Mel.
81? No.
Good. Powers
Yeah.
of 5. Powers of 5.
5, 25, 125.
And why is there never any overlap?
Because all like the powers of a prime don't have the other primes as factors.
That's right. 625 only has 5 for factors. 81 only has 3 for factors. But now, Riken, what's your concern?
There's going to be gaps. You're not going to fill all of the counting numbers. Like you can't make every counting number that way.
Nathan?
like in the very first example we didn't fill 1, and technically it's the same size, so you don't need to fill every room. You just have to have a way to assign every person to a room.
Okay.
Could we make the ones that don't fit their own set?
You both make very good points. Nathan pointed out that yesterday we had that pesky 1 that never got chosen, right? And that we don't really need to fill the hotel. We just need to find a room for all these people. If it leaves a bunch of rooms empty, like as a matter of fact, 15 would be empty under Riken's description. That's fine. We've still gotten a room for everybody. And so we're okay. We don't have to fill every room. But then Lauren points out, we could put 2 to the powers here, 3 to the powers here, 5 to the powers here. And this one could be all the other numbers that aren't powers of primes. Numbers like 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. We could make them their own set, right? We don't have to, Nathan's right, but we can, Lauren's also right. Does that make sense to anybody besides Yoga, Riken, Nathan, and Lauren? Does it make sense to you guys? So now we have sort of powers of prime. Notice, this depends on the very first thing we proved in this course. What was the very first thing we proved last Monday?
That there is no largest prime.
That there are infinitely many primes, right? We need infinitely many primes in order to do this. If there's a largest prime, then this process runs out and we can't break it up this way. But the fact that the fact that we proved last Monday is crucial right here. Somebody's coming back. Charlie.
Could you also do like each prime starts its own set and then the largest multiple of prime of a number, then it's added to that prime set?
Multiple of prime or power of prime, Lauren?
Largest prime multiple.
Okay, I'm not sure I understand what you mean. Let's try it. So we put a 2 here and a 3 here and a 5 here. Is that what you mean?
Yeah. Yeah.
Who's here?
4.
Here?
I think it would be 8. No, 8. Yeah, 8. It's like, so like 6 breaks down into 2 and 3, so you'd put it into 3 because 3 is the largest prime multiple that you can break it down into.
Okay, that's what you meant. Prime
Yeah.
factor.
Yeah.
So every number here gets paired with the prime, which is its largest prime factor. So 4, 5, 6 goes here, 7 goes here, 8, 9, 10 goes there, 11, 12, 13, 14 would go here, 15, 16, yeah, I think that would work, Lauren. I like it. I think that would work. Which is a nice segue, because what I was about to say was, in my experience, these two right here are the most common ones. But I know that some of you guys have studied this before. Poor Charlie. And I'm just wondering if anybody has seen any other methods that would do the trick of pairing this array with this line. Lauren's just given us one. I don't think she's seen it before. I think she just kind of made it up just now as kind of a take on a way to solve Yogev's problem of multiples. But has anybody have another way to do this?
We could do the powers of primes like from the other side, right? So if each column has the powers of one prime, then we could say that it's like the first row has all of the primes to the first power. The second row has all of the like perfect squares of primes, and the third row has all the perfect cubes of primes.
Yes, yes, that would work for sure. Anybody else? As a fact of transfinite arithmetic, notice that this says that infinity times infinity, sorry, aleph times aleph, aleph squared is equal to aleph. What does it say about aleph cubed?
Wouldn't that just like, if we're thinking about this like on like a plane, or wouldn't that just like add another dimension?
It would. Is it bigger than aleph?
No, because that's just aleph squared times aleph, which is aleph times aleph, which is aleph.
Good, good. So we can take the cube and break it up into the square times the 1. This, we know, is just aleph. So the whole thing is just aleph. Yes, exactly. That means,
So Aleph acts a lot like 0 when you multiply it.
it does. So 0 is called the annihilator. That root means,
So nihil is like nothing, so it's like to make nothing, maybe.
yes, it's the nothing maker. And aleph, it doesn't make a thing nothing, it makes a thing infinite. Or it just absorbs any finite stuff into itself. So far, n plus aleph equaled aleph, n times aleph. Actually, let me write it this way. And the next thing I write is
Aleph squared?
no. What's the next operation? Plus, times,
Would be aleph to the power of aleph. Aleph raised to the power.
you guys okay with that symbol? You know what that means?
So that putting it to the power of aleph?
Yeah, it's-
To the power of, but not aleph, that's an n.
So then, what would happen if we raised aleph to the power of aleph? Would that still equal aleph?
Well, I think it should, because you can still do like the pairing for squared. Say they're equal aleph, and then just keep going from there to infinity.
Well, that's not the next operation yet. Aleph to the aleph is not the next operation. Maybe it is, maybe it is. Aleph plus 1, aleph plus 2, aleph plus 3, dot, 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 aleph plus aleph is the same as aleph times 2, aleph times 3, aleph times 4, aleph times 5, dot, 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 aleph times aleph is the same as aleph squared, aleph cubed, aleph to the 4th power, aleph to the 5th power, dot, 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 aleph to the aleph power is the next one. But we actually do something different before we get to aleph to the aleph. We're going to look at something different first. This is actually, I want to do something first, and then I want to address that question. How you doing, Charlie?
Sorry, my computer is just not happy with me today.
I'm having a tough day.
Hopefully it'll stay now.
Luckily for you, I'm doing the whole thing, so I'll send it to you after class.
Okay, thank you.
The rational numbers. What do I mean when I say the rational numbers?
Numbers that either terminate or are infinite in a predictable manner.
Well,
It can be represented as a fraction.
okay. So there are two ways to characterize the rational numbers. One is to say decimals, which either terminate or, and then to say that they go on forever in a predictable fashion, that's actually not correct. Let me show you this decimal. Thoroughly predictable pattern, yes? But not a repeating decimal. It's a pattern, but it's not the same thing over and over again. This number is not rational. This number is irrational. Okay, so it's decimals which either terminate or repeat. Those are the only two options. This guy is not rational. And then the other characterization, which I heard somebody say, is fractions. P and Q must be whole numbers, positive or negative. The fraction can be thought of as being reduced, but it doesn't have to be reduced. So these are the rational numbers. We give them the symbol Q for quotient because they're called fractions or ratio. So now let's set the scene. You're working at your hotel. Business is good. Life is good. Business is so good. You're able to sit back and watch a little TV. Your hotel business is so good. It has infinitely many rooms. And everyone is full. You've rebranded the hotel. It's no longer the Hotel Infinity, it's Hotel Aleph. You're working late one night. When up pulls a car. It's a very crowded car. It's a very full car. inside this car is every rational number. Every number which can be expressed as a fraction. Every terminating, every repeating decimal. Every whole number, every integer. All fractions, all rational numbers. And they want a room in your hotel. Can you fit them? Or you turn them away and face the monster that Peyton warned us about yesterday, that in fact, this infinity is bigger than this infinity. What do you say?
Could we apply the same method that we did yesterday? Move them down and just assign them a number? Does that still work?
You tell me, how far you?
The problem,
Hang on. You might as well assume the hotel's empty, right? Because we
Yeah.
can empty out infinite many rooms, right? So
Yeah.
you don't have to worry about moving them down or anything. The hotel's empty. How are you gonna assign the fractions to rooms? Mason?
We have to, okay, so why can't we just pair in the fractions to the individual counting numbers?
Tell me what the pairing method is. Tell me the formula.
What the method would be?
Yeah,
Oh, the denominator would go on for Aleph.
with numerator.
That's interesting. Once again, I was thinking finitely, not alephly, I guess.
Do we have to keep the fractions as fractions, or can we like assign them each a number or a letter or something?
Well, you can assign them anything you want as long as the assignment is deterministic and finitely calculatable.
The main issue is that we need to have them, it's a deterministic value, like you said. We have to give it some calculatable way to figure this out.
or perhaps there is a larger infinity at hand, and because of that, we could not incorporate it within the current set.
But remember, that was Andrew, wasn't it?
Yes.
Remember, Andrew, you don't get off the hook that easily. You have to prove that there's no way to pair this set to this set. You have to prove that any possible pairing would fail, right?
Okay. All right.
I think
sounds
it's
like
time
proof
for
time.
an attempted indirect proof. That sounds like the way to go here.
Indirect proof time, my guys.
Or like we try for an indirect proof and we might just directly prove something like we did last time.
Yeah, but I say last time we proved that there was no larger infinity. But I guess things are changing since we're throwing the pesky rational numbers into the mix.
So what would this be like? Like if we were to draw this into like the lines again, what would it be? Because I don't know. I'm just having like some trouble
It's like
visualizing
imagine.
it.
I think as far as I can visualize, it's two different one-dimensional lines. It's just that the rational number, like we have counting numbers 0, 1, 2, 3, and then rational numbers, which include like 1/4, 2/4, and then like every fraction.
I guess maybe you could think of it as like the denominator and then numerator, like those two as two separate lines, each of them going on for aleph, then you should be able to fit every value within that like plane.
This
Peyton,
part.
Peyton, say all that again, would you?
So if you think of like the numerator as one line and the denominator as another, and both of them go on for aleph, you should be able to fit all the rational numbers.
Yes. And then the only thing we haven't talked about yet, we've had talked about adding and multiplying and the power of. I don't think we've ever talked about finding the quotient of aleph.
Oh,
That's one thing we've never talked about, something that's been
Wait.
bugging me. We've always skipped subtracting and dividing or even finding the square root. We've never we have not breaking apart aleph.
Well,
Yeah,
yeah.
by
Wait,
Peyton's
if each-
explanation. Oh,
If
By
each
Peyton's
part of the fraction,
trying to subtract. In theory, you could look at it as the same way as adding, and it should be the same, right? Like just from like what we've seen, like aleph minus 1. But then if you actually try to like subtract aleph from aleph, it gets really confusing in my opinion, because aleph equals aleph plus 1, right? Or 1 plus aleph. So aleph minus aleph can be anything then, right?
I don't know, but if the numerator and the denominator are each like sequences their aleph long, can we just set all of the rational numbers up as an array where we can like, you know, correspond to each one, just a two-dimensional array like we were doing with the last
That's what the
thing?
numerator and denominator thing was, I thought.
Yeah,
So the only thing I could think of with the problem with that is that you'd have like 1/2 is the same thing as 2/4. So you'd have it written multiple times. By every rational number, does it want you to have numbers that are equal still?
Okay, let's take a pause for a moment. Riken, you've made a concrete suggestion. Let's carry it out and then within it address Charlie's question. So Peyton says the numerators are aleph many, the denominators are aleph many. Riken takes that and says something about a two-dimensional array. What do you have in mind, Riken? Can you give me the list?
like put all of the counting numbers on one side, like as the columns, right? And then all of the counting numbers as rows. Yeah. And then put the column numbers over the row numbers, or either way, shouldn't really matter.
So we better not have 0 in the denominator, you think?
Right. Yeah, that's probably not a good idea.
Okay, so tell me what goes here.
0. That's all zeros. So it's 0 over every number.
Give me a fraction.
0/2. Oh, well, not right of that first 0.
What goes here? 0/1.
Yeah.
And here?
0/2.
So these are your numerators? And these are your denominators?
Yeah.
So 0/3. What goes here?
1/1. 1/2. 1/3. 2/1. 3/1. There, yeah.
I feel like if we can prove this is does fit, we might be able to use it for like saying aleph divided by aleph is still aleph, because by Payne's explanation, it's aleph over aleph is this rational number. If we can prove that that's aleph amount, then maybe we can use that as a new rule.
What if we took aleph times aleph equals aleph and divided it on one side? We would see that aleph divided by Aleph would still equal Aleph. Does that make
Under the
That just
same logic, you could get Aleph over Aleph times Aleph equals 1 over Aleph, which is 0.
Yogiv and Mason are trying to push our transfinite arithmetic rules based on what's happening here. But let's make some sense out of this first before we try to make some rules from it, okay? Let's figure out whether this makes any sense, and then we'll go back to the arithmetic question, okay? So let's first address Charlie's question. Charlie, what happens when we do this? What do you see in there, Charlie?
A lot of these numbers are the same number.
That's right. This whole column is the same number, right?
Mm-hmm.
This number, this number, this number, they're all equal to 1, are they not?
Mm-hmm.
There'll be repetitions all over the place. Yes?
Now, in theory, because they're repeating, that wouldn't mean that there would be not enough rooms. That would mean there would be like multiple rooms for the same number.
Good, good, good. So Charlie says there's repetition, and then she immediately gets to the point that that's not a problem because if we can fit all of these fractions into these rooms, then we'll actually have fit a quote unquote bigger set than the rational numbers because we'll give 1 infinitely many rooms over here. We'll give every fraction infinitely many rooms over here, as a matter of fact, because we'll give every possible representation of it. So it's the reverse of a problem. It would be a problem if we needed multiple rooms for 1 fraction. But in fact, we have multiple fractions for rooms, so we're okay. And by the way, let me just say what you probably already have said. This 2-dimensional array, we know we can fit in here because we just did it at the start of class, right? The 2-dimensional infinity question is a settled fact. We know how to handle that. In fact, we had 3 or 4 different ways to do it. The marching band, the powers of primes, Lauren's way, Charlie's way, etc. Okay, so let me say the fact here. Let's say the size of the counting numbers this set right here is the same as the size of the rational numbers. Let me just take a step back for a moment. I really liked the way that happened. Peyton saw something about numerators and denominators, kicked it around for a little while. Somebody said something, I forget who it was now, I apologize. Riken came up with this array and said it's just an array going into 2 dimensions. It was really cool to watch you guys talk. I was quiet for a minute there and just watching the ideas bounce around on my screen. Somebody proposed that it was going to be impossible. Somebody threw some ideas out, and then this came up. It was very neat the way you got to this. Nice going. But one of the things something I want to point out here is rational numbers. That's a huge set of numbers. A huge set of numbers. The fractions between 0 and 1. Just look at the ones between 0 and 1 for a moment. Don't even look at all the ones between 0 and 1. Just look at 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, etc. Just those fractions alone are obviously the same size as the counting numbers. And then you go 1 1/2, 1 1/3, 1 1/4, 1 1/5, 2 1/2, 2 1/4, 2 1/3, 2 1/5, 2 1/6, 3 1/2, 3 1/3. There's a sequence this big between 0 and 1, between 1 and 2, between 2 and 3. And there are way, way more fractions than the ones I've named. There are a lot of fractions. Between any two fractions, there's another fraction, right? Take any fraction, 115 over 7,012. Take another fraction, 233 over 9,998. Average them. You get a fraction. Average those, you get a fraction. Keep averaging. You get fractions. Between any two fractions, no matter how close together. 1 1,000th and 2 1,000ths. There are infinitely many fractions. And yet still with all those fractions, there are no more of those than there are counting numbers. Because we can pair them up and all those fractions can fit into your hotel.
I have a question.
Hang on, let me just say one more sentence, then that'll shut up. A set which seemed like it was finally going to be so big, it gave us a new size of infinity, is really no larger than Aleph. Mason, question.
So,
Mason, wasn't it?
yeah, so when you said that we had, first we have, an Aleph many in between 0 and 1, and you said it kept going down. The first thing that popped in my head was Sierpinski's triangle.
It's fair that sequence. Well, that sequence isn't geometric. This is not a geometric sequence.
No, it's not. It's not. But that was just something that I was like, that's something that just popped in my head of, oh, that's interesting, Sierpinski's triangle, and then seeing 0 in between only 0 and 1.
Yeah.
And how it just kept continuing to Aleph over Aleph in between each number.
And we do have to be a little bit careful because we're bumping up against some stuff here that we don't really understand, that you don't understand, and I haven't talked to you about it yet. So I don't want to go too far and say too much. I didn't give my television legs. I apologize. It was sitting on the floor. Other comments about what I just said, and then let's talk about arithmetic. So let's talk a little bit about arithmetic. First of all, the thing to realize is there's no such thing as subtraction. There's no such thing as division, and there's no such thing as exponentiation. Those are all ghost operations. Subtraction is just adding a negative. Division is just multiplying by a fraction. Rooting is just exponentiating with fractional exponents, right? So we don't need those operations. They're just there for convenience sake. Okay. Secondly, and I couldn't tell where Nathan was heading with this, division with Aleph is tricky because typically we would think of division as breaking something into pieces, right? 10 divided by 5 is taking 10 things and breaking it up into 5 pieces, the same size, and saying how many in each piece. When you start dividing Aleph up, you take this thing. So what's Aleph divided by 2? Well, you divide it into 2 pieces the same size. You might think the evens and the odds. So Aleph divided by 2 is Aleph. Divided into 3, Aleph divided by 3 is Aleph. So is Aleph divided by 4, so is Aleph divided by 5. And now we're starting to see, like Mel saw, that Aleph behaves in some ways like zero. Arithmetic with Aleph, arithmetic with zero is boring. The answers are always just Aleph, or the answers are always just zero. Until we get something like Aleph divided by Aleph. How do we divide Aleph into Aleph many pieces? Well, Lauren pointed out a little bit ago that that's effectively what we did with Charlie's evens solution. And we came up with essentially that Aleph divided by Aleph was Aleph, which makes division with Aleph really boring. And then I thought I heard Nathan's talking about something like 1 divided by Aleph. And what meaning does that have? Well, you're going to take one thing and divide it into Aleph many pieces? We have to figure out what it means. Okay, it's a little after 11. We're going to start something new here momentarily. In a moment, I'll send you on a short break. But first of all, any questions so far?
We kind of been like talking about this in the chat, but would there be a way to assign irrational numbers to the counting?
That's after break. That's exactly what we're going to address after break.
Oh, also a question. So, how do we get that Aleph divided by Aleph equals Aleph if they're the same thing?
Because we take a set with Aleph many members, like the counting numbers, and divide it into Aleph many pieces, like the powers of 2, the powers of 3, the powers of 5, the powers of 7. And then we say how many in each set. And the answer is Aleph. So you guys don't know calculus yet. You're going to learn that questions like this fall into a category of questions that are known as indeterminate forms.
So it's like 0 over 0?
It's 0 over 0 can be an indeterminate form. Yes. And the answer to these questions vary depending upon how you arrived at that infinite sized object. Infinity divided by infinity might be infinity, might be 0, might be 2, might be 5, might be 11. Who knows? It changes. It's indeterminate, and we need finer techniques to answer these questions, and you'll learn them in calculus. Jack, were you trying to say something there? Okay. Let's take a brief break, come back, I'll erase the board, and we'll get started on the second half of the class.
That was me humming. Yeah.
Welcome back, Jack.
Thank you.
Nathan, I love the little screensaver on your Zoom. Little circles that go spinning around. What's up in the chat? So if you haven't had the chance to look at the chat yet, probably now is a good time. Yogiv is the first one to raise the question. At 11 a.m., he says, what about irrational numbers? Would those fit? And Andrew Shelton says, if there are infinitely many rooms, then why not? What assumption is Andrew making there when he says that? Is Andrew with us?
He's assuming all of the infinities are the same size.
That's right. That's right. Andrew's answer assumes that infinities are one size fits all. Do you see that, Andrew?
Yes, yes, I do.
So Yogiv is proposing that if you're looking for an infinite set which is bigger than the ones we've encountered so far, what about the irrationals? And Andrew says, well, they're the same size because there's only one size of infinity. And then Yogiv says very, very, with great insight, he says, then what's the function? What's the pairing function? Essentially challenging Andrew to prove that the size of the irrationals is the same as the size. Now, when he says a plane here, I assume he doesn't mean an airplane or anything like that. He means, can you take the irrationals and put them into a two-dimensional array? Because once we see them as a two-dimensional array, we know that we can fit them into the hotel. Which is exactly what Peyton says. So Yogiv's question at 11:01 and Peyton's question at 11:02 are essentially phrasings of that same question. And then Riken thinks he knows the answer and he says, that's the problem. Andrew Shelton, that last question is an interesting question. Are there an infinite number of irrational numbers? Are you thinking that there might only be a finite number of irrational numbers?
Well, possibly. What I was going at from there is that the most common irrational numbers that come to mind for me are going to be, pi, e,
Time
like the
out,
one,
time out.
you showed.
Okay, let's think about pi. How about pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi? They're all irrational, right?
Yeah.
And there are certainly irrational, certainly infinitely many of them, yes?
I suppose so, yes.
Or how about square root of 2, square root of 3, square root of 4, square root of 5, square root of 6, square root of 7, square root of 8, square root of 9, square root of 10, square root of 11, etc. And we could throw a bunch out. We could throw
Okay.
out square root of 4 and square root of 9. But all the rest would certainly be irrational, right?
Yeah, so there are quite a few irrational numbers. Kind of the problem now that, listening to you break it down like that, you can't really put those into a plane because kind of like, where do you start? Like, do you start at pi? Do you start at square root of 2? Like, what's the smallest? And then, I mean, based off of that, it seems like there would be an infinite amount of irrational numbers.
Okay, so there are two things I want to address in what you're saying. We no longer say things like there are an infinite number of them because we have more precise ways of saying it. Are there Aleph many irrational numbers? Is the way you want to phrase it. Are there more than Aleph many irrational numbers?
I thought Aleph referred to the counting numbers.
It does. It does. In Aleph,
an irrational number is not a counting number.
No. You're confusing again the numbers themselves with how many there are. Aleph is the size of the counting numbers.
Okay.
Maybe it was Mason that I was talking with this. Who did I ask his shoe size yesterday?
That was me. But
Yeah.
yeah, it's essentially the set, not what it is. It's just the amount that's there, not the precise or what it is.
So Aleph is not an irrational number. Aleph is not a counting number. Aleph is the number of counting numbers that there are.
Okay.
So
all right.
There are exactly Aleph many rational numbers. We proved that a moment ago.
Okay.
There are at least Aleph many irrational numbers.
At least.
The multiples of pi. There are Aleph many multiples of pi.
Oh, okay. Yeah.
Right? The question is, are there actually more than Aleph many irrational numbers?
What if we multiplied Aleph times an irrational, like pi?
You'd get Aleph.
You just get Aleph again, even though it's not so that our rule is for any finite number.
That's right. That's
so
right.
It doesn't matter if it's an integer, it doesn't matter if it's rational, it doesn't matter if it's a whole number, nothing. As long as it's a finite number.
That's correct.
And then it doesn't matter if it goes on for Aleph, because then it's just Aleph times Aleph, which is Aleph.
No. The length of pi has nothing to do with how big pi is. Pi is less than 4. The fact that it has infinitely many decimal digits doesn't make it Aleph size. It's less than 4.
So that repeating that decimal doesn't make a difference to us.
No, not in doing arithmetic with Aleph. No.
Yeah, that's the only time it doesn't matter. Okay.
Correct. The other thing I wanted to address to what Andrew said was, he said something to the effect of, I wouldn't know what, you wouldn't know where to start. Do you line the pies up first, or do you line the square roots up first, or do you line up multiples of E? I don't know where you'd start, so there must not be a way to make it into a plane. Saying that something is hard is not the same as proving it to be impossible. We can't just make a couple of attempts, throw up our hands and say, oh, well, I guess it's impossible. We have to prove that no such pairing between the irrationals and the whole numbers would exist. And that's hard. Proving impossibility is a very difficult task. Good questions in the chat, guys. Anything else?
I mean, I suppose could we like make an irrational number line
What
and
do you
then
mean?
compare that line to the Aleph line?
What do you mean by that?
So I'm sorry, I meant like so the 0, 1, 2, 3 going on for Aleph many terms number line, and like, and then like say like put that as the numerator, and then you have all the Aleph, all the irrational numbers. Of course, I don't know how you would put those in any type of order, but you know, you could just have them underneath your other numbers, and then trying to think how you'd compare those.
It's the, of course, I don't know how you would put those in any kind of order. There's the rub, as they say in Shakespeare.
Could you make, so like, could you put the numbers between 0 and 1 and have that be a column, and then put the numbers between 1 and 2 and have that be a column?
Well, it's funny you say that, Charlie. What I was about to say was, well, first of all, let me say that what we did yesterday and what we did today, a total of 4 hours of class, if we were on campus in a classroom at regular MSA morning classes are 3 hours long. What we're trying to squeeze into yesterday and today, 4 hours, would probably take us about 3 days on campus. So we're trying to squeeze this in pretty tight. We are not going to finish it today. We're going to have to go into tomorrow. We've only got about a half an hour of class left. But the other thing I wanted to say was there's a fair amount of, I don't know, kind of background mechanical foundation we have to set up before we could move forward. So I need to spend a little bit of time doing some things with you that are going to feel like side stuff for a little while, but it's machinery that we have to develop in order to address this question. And Charlie has actually hinted at a bit of it. So I think I'm going to go into that mechanics right now. And it has to do with the 0 and the 1 question. Let me change my camera back to the board. Okay. So. What word am I gonna put here?
Aleph long? Or
I could-
Equinumerous.
Yes. That's what I'm looking for. A little while ago, as Andrew was kind of struggling with the irrationals, he said something like, of course, I don't know how you list the irrationals. We have a word for that. When we can make a list of them, which is essentially anything that's Aleph sized. In mathematics, we say that set is countable. Or we say they're denumerable. That's a funny word, which essentially says you can make a list of them. Or we say they're countably infinite. All of those phrases are synonymous with Aleph many. Then the question that was posed in the chat was, what about the irrationals? And actually, that's not the question we're going to address yet. We're going to go all the way up to the real numbers and say, what about the real numbers? And I'll explain why. First of all, once upon a time, kids learned all these sets of numbers in school. They learned things like the whole numbers and the integers and the rationals and the irrationals and the reals. I'm not sure whether kids learn that anymore. So we're throwing around the rationals and the irrationals, and now I'm bringing in the reals. Does everybody understand what those words mean? Or does anybody need those words explained to them? So the rationals are fractions. It's where the word comes from. It also means decimals which terminate or repeat. Irrationals are what? So we've been throwing that word around for a few minutes now. Could somebody explain what irrational numbers are?
numbers that can't be represented as a fraction or they do not terminate?
Unfortunately, the definition here is just ones that aren't rational, right? Numbers that can't be written as fractions, which don't terminate or repeat, right? The familiar ones to you guys, Andrew named a few: pi, e, all the square roots that aren't perfect squares, right? But also, I gave you that one a little while ago, this one. You could sit there at your desk right now and make up any number of decimals, kind of like this, that just go on forever. My favorite. Non-repeating, non-terminating decimal. Goes on forever. It's irrational. okay? And then the reals. So this is called Q. The irrational don't really have a symbol. We often use R, a boldface R for the reals. What are the reals?
They exist on the number line.
Good. They're points of the number line. In terms of rationals or and irrationals, reals are simply anything that's either rational or irrational. Now, Yogiv's question at 11 o'clock in the chat was, what about the irrationals? I said, we're not going to address that. We're actually going to say, what about the reals? See if you can do this. Explain why answering the question about the size of the reals will also answer the question about the size of the irrationals. Who can do this? Who can settle this? Who can explain this?
Well, the irrational numbers are real numbers, so they are basically like the same set, just one has even more.
Yeah. Same
So, if real numbers are both the irrational numbers and rational numbers, so if the irrational numbers are the same size, Aleph size, we already know Aleph plus Aleph equals Aleph, so we would expect our real numbers to be Aleph. There be Aleph many real numbers, but if there are greater than Aleph many real numbers, then we know that we're going to have greater than Aleph many irrational numbers, because Aleph plus anything smaller than Aleph, which we've already proved, is Aleph.
Okay. Who was talking? It was Mitchell, wasn't it? Mitchell, the second half of your statement was completely correct. You said if we have more than Aleph many reals, then there must be more than Aleph many rationals, because if there were only Aleph many there must be more than Aleph many irrationals, because otherwise Aleph plus Aleph would just be Aleph. The first half of your statement, I think, though, was reasoning in the wrong direction. So the second half of your statement was, if the reals, I'm being sloppy in my language here, Mason, so don't hold me to this symbol. If the reals are Aleph many, then the irrationals are Aleph many. But that's the second half of what you said, Mitchell. The first half of what you said started out with a statement about the irrationals and concluded with a statement about the reals. Turn your reasoning around, could you please? No, sorry. Mitchell said this. Explain that, Mitchell.
So if our reals, like the size of that set is Aleph, so we already know that there are at least Aleph many irrationals because we can just do 1, 2, 3, 4 times pi and all those. So we know that there's at least Aleph many irrationals. So if there are Aleph many reals, then the irrationals are also Aleph many because Aleph plus Aleph equals Aleph.
All right. So based on what Mitchell said, we're only going to look at the reals. Now let me go back to something Charlie said. Charlie was talking about from 0 to 1 and from 1 to 2 and from 2 to 3, etc. Check out this fact, please. Can anybody prove this fact?
Didn't we just prove this with rationals? How there's an infinite, there is a Aleph amount of rationals, so there would be an infinite irrational between the two.
This isn't talking about rationals. This is talking
Just
about
points.
all real numbers. Points on the line. This is potentially more than the rationals. Does anybody know how to prove this fact?
So, well, we did like going back to like the hotel thing when we made them fit. Like,
No, let me interrupt you, Lauren. This is a totally new fact. Because this is talking about points on the line.
Would this get?
This is a way, way bigger set than we've been talking about before. Everything we've talked about before, we could list. Points on the line, we don't know whether we can list or not.
So if we don't know if we can list them, we don't really know if we can map them to each other
That's not true.
yet.
No.
It's probably if we're gonna see if we can, it probably has to do with trying to map it 1 to 1. That's probably the best way to prove if they are equal.
Okay, so Nathan is saying, can we map this set to this set? Is there a function that pairs this interval to the entire line? You guys know about domain and range. Do you guys know about open intervals? Do you guys know interval notation? If I write something like this down, you know what that means?
Yes.
So we want to function with domain this and range that. And pardon my use of that sideways 8. I'm pretending I'm in school math now. Can you give me a function with domain here and range there, or vice versa? It doesn't matter. Nathan, do you know one?
No, my first thought is the 1 over would get you quite a lot, I think.
This guy?
1 over would get you that portion, yeah. It's not quite all of it yet.
Maybe absolute value of 1 over.
It's already positive, that's just the same.
Could you do something that looks like tangent? Like cubic looking tangent, but like only from 0 to 1.
Yeah, that'll do it. That'll do it, Lauren. Something that looks like tangent only from 0 to 1. Why is Lauren's idea a good idea? What does tangent look like, guys?
It has asymptotes, so
It's asymptotes. So it's not going to be exactly tangent. We're going to have to squeeze the tangent between 0 and 1, right?
Oh, no.
So we know we can do that. We can squeeze our stretch functions as much as we need to, right? Well played, Lauren. Does everybody see what's going on here? Please say something if you don't get it. This is our new question. This interval shows up at your hotel and they all want rooms. We good? Let me give you a new bit of mechanics. It's a fact. I gave it this name. I don't know what everybody else calls it. I call it the fundamental counting principle. You know the fundamental counting principle, even if you've never heard this name. Here's the deal. You wake up in the morning and you go to get dressed. In your dresser, you have 3 pairs of socks, 5 pairs of shorts, and 4 shirts. And you're a nerd and you're on Zoom all day, every day anyway. So you don't care if they go together or not. You'll wear them in any combination whatsoever, right? Look at me. I didn't pay any attention. I just got dressed this morning. How many different outfits could you create?
60.
60 separate outfit combination.
Right? You have 3 decisions to make. This decision gives you 3 options. This decision gives you 5 options. This decision gives you 4 options. The total number of possible outcomes is 3 times 5 times 4 is 60. You know this fact, yes? I don't know if you call it that or not, but you know it. You think about it every time you get dressed in the morning. Let me explain why I bring it in. Let's say I want to make a real number. And I want to make a real number between 0 and 1 by creating its decimal expansion. I write down a decimal point, and then I have a decision to make. My decision is, what's going to be the number in the first decimal place? How many options do I have in deciding what that digit's going to be?
9.
10.
And
And 0 through 9.
0 through 9, if you count 0, which we do,
10.
there are 10 possibilities. Yes? How many options do I have at my second decision?
Also 10.
Also 10. And the third?
10.
And how many decisions do I have to make?
10 to the Aleph.
Not. How many possibilities total? How many decisions do I have to make?
Aleph.
Oh, decimals there are, or digits.
Okay, you guys are breaking up. I don't know that I've heard a clean answer yet.
Aleph amount of decisions.
Who's talking? Is that Andrew?
Yes.
I have Aleph many decisions to make. Each decision presents me how many options?
10 options.
10 options. 10 options. Now, by the way, why is it 10? Because we're in the decimal system, correct? We could just as well be in 16 decisions, or sorry, 16 options, or 2 options, or 3 options. We could be writing it in binary, right? So this could be 2. Doesn't really matter. Presents me 10 options. Thus, I have blank possible outcomes. In other words, there are blank, these two are the same, many real numbers between 0 and 1. Fill in the blank.
It's 10 to the aleph. I know that.
Look what's happened. This has been our arithmetic. And so far, Aleph's been very boring. All of these have produced Aleph. Somebody said, well, then the question is going to be, what's Aleph to the Aleph? And I said, well, actually, we're not going to get there just yet. We're going to answer a smaller question. The smaller question we're going to consider is not what's Aleph to the Aleph, but what's 10 to the Aleph. But I said a moment ago that 10 is just because we're in the decimal system. We could just as well think about what 16 to the Aleph is, or 3 to the Aleph, or 2 to the Aleph. And I actually better put that down here. Oops. That mostly we're going to ask this question. 2 to the Aleph. What does 2 to the Aleph equal? So essentially, we're going to say a 0 or a 1, a 0 or a 1, a 0 or a 1, a 0 or a 1. How many numbers could we get? Somebody said, what about terminating decimals? What about terminating decimals, guys?
They just end in zeros. You just keep on getting 0.
Yeah, terminating decimals, that just means that from some point on, all our decisions are zeros. What's the next digit? A 0. What's the next digit? A 0. What's the next digit? A 0. By the way, we do not allow, for reasons you should know, repeating 9s. If somebody wants to give you we don't allow that. We simply say, hey, make that a 9 and make the rest zeros because it's the same number. Okay? In binary, we don't allow repeating 1s. Repeating 1s are the equivalent of that. I hope you're getting all this in your notes because this is it's a ton of kind of boring stuff that we have to know before we can go on. We're not going to finish everything today. I'd kind of like to finish the boring stuff today and start up again tomorrow, but you're going to have to know all this stuff tomorrow.
Can you know the side note, but could you prove that 2 to the Aleph equals 3 to the Aleph equals 4 to the Aleph equals? Because it's just the number of like decimals from 0 to 1 in any base, which should be equal.
Yes, yes. These are all equal. What they are, we don't know, but we do know whatever they are, they're all the same. And your reasoning is perfectly valid. They all describe the number of real numbers between 0 and 1, just written in different bases. And writing numbers in different bases doesn't change how many you have. Okay, let's see if we can squeeze in something in the next few minutes. Subsets. Subsets are sets contained within other sets. Okay, so what are the subsets of this collection?
Triangle and circle.
That's one.
Square and
And then
circle.
circle and square, and then triangle and square.
Mel, I didn't hear you.
The last one's triangle and square.
Can you have a set of just triangle? And then just circle and just square.
There are two you're missing.
Does the order matter?
No. Good question. The two you're missing are subtle. They're kind of trivial.
Can you have one with none of the shapes?
That's right. Good. Here's one.
And
then
then
all of
again,
the
one
shapes.
with all shapes.
How many were there? How many are there?
8.
8. Why 8?
Because you've got 3 like terms in the set.
How do you get 8 from 3?
2 to the
2 to
power
the
of
third. Yeah.
And why is it a 2 to the question? Where's the 2 to the in this?
3. Each one you choose either to have it or not.
Good, good. Essentially, we ask ourselves 3 questions. Do I include triangle? Yes or no? Do I include circle? Yes or no? Do I include square? Yes or no? So once again, I have 3 decisions to make. And at each decision, I have 2 options. Yes? Does that make sense? So in a sense, these are binary numbers. This is the binary number 0, 0, 0. No, no, no. This is the binary number 1, 1, 1. Yes, yes, yes. This is the binary number 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1.
Could you also do 3 factorial plus 2 for the empty and then all of them?
So you could, but that formula won't work every time. The formula 2 to the power of n, where n is the size of the set, always works.
Okay.
take a screenshot of that. That's where I want to start tomorrow. I'm not going to go back to my other camera because I know you're writing all this stuff down. So I will say, have a good afternoon. Afternoon program today is on the Innocence Project, which is a really interesting organization. Hope to see you there. I will see you tomorrow, 10 o'clock. Lauren, remind me and I'll record it for you. And Charlie, I'm going to send Eli the recording of today's class. I'll also send it to you.
Thank you.
All right.
Thank you.
See you guys.
Thank you.
Thank you.